Hello and welcome all to the Reducing Cost of Tests of In Circuit Test for High-Mix Low-Volume PCBA. Today we will hear a presentation by John O'Connell. My name is Derek Ong, the EMEA Market Development Manager, and I will be your host for this web seminar. For everyone's comfort, this is a lecture-style meeting. However, you can still send questions in writing at any time during the session through the Q&A functionality of the WebEx meeting. We'll do our best to answer your questions after the presentation, but may have to come back to you after the session if we haven't been able to. While the answer to your question may be published for others to see, we will keep your identity private. Please be reminded that this webcast will be recorded so you can review and share with your colleagues at any time. So without further ado, now I'd like to hand it over to John for the presentation. John?
Thank you, Derek. And thanks to everyone for joining on the line today. In today's seminar, we're going to look at some of the techniques used today in low volume and high mix manufacturing. And we're also going to examine what other strategies we might employ to lower our costs in manufacturing. So here we can review what are the requirements of today's high mix and low volume production. Compact size electronics products still rely on a functional test, that's for sure. All our products are still electrical in nature. But with better accuracy and placement of SMT machines, more advanced techniques available, quality has improved. However, the ability to introduce defects has also increased with complexity. And traditional in-circuit test does have its place in manufacturing. It's used commonly, but it does have challenges to be cost effective in a low volume and high mix environment. So what challenges do we have in being able to improve test? Historically, it's difficult to make investments ad hoc. We have to sometimes make do with what technology and what investments have already been put in place. And this puts in a squeeze on the equipment that we do have to try and make do. And often you see in low volume manufacturers that they have to use non-optimal test platforms that they have just inherited in order to squeeze everything from their existing or previous investments. Ultimately, you can end up moving to multiple customer-specific test stages, and each with their own different user interface, each with their own test coverage, but also with their own defect spectrum. And every one has also a cost associated with it. We see that very often, because of this mindset, there's no clear vision or commitment to test stages to address for the longer term. And test strategy is sometimes done transactionally. With each win cycle of new business, maybe there's some small investments allowed. And also, test economics is not always seen as the best place to invest capital equipment. We also see influences from our end customer on platforms of choice. And this sometimes ends up that we have to make do with what equipment's been handed to us. So what do you see when you look around your test area? Do you just see a flexible and capable test department, or just a collection of random instruments? We hope that some of the points reviewed today will help build arguments to review your current test strategy and choices. So what can we employ? What tactics or strategy can you employ to lower the cost and optimize the test coverage? Well, rationalizing test stages, removal of excess stages. Try and look at what are the latest test techniques. Refresh and upgrade platforms so we can really extend the coverage from single platforms instead of multiple platforms. So simplify the test stages into one platform. If we do that, test stage simplification and standardization minimizes the engineering effort. One other opportunity is to lower our tooling costs. So lower the costs that we spend onto in-circuit test type fixtures. Can we reduce those costs with new techniques onto one platform? If we're going to make an investment in tooling, how can we make it an optimal investment? Another topic here that we're going to examine is the use of engineering resources. Sometimes this is underestimated by engineering management or operations management, the investment and time it takes from engineers to actually turn on a new strategy or get that extra coverage. It's very often the engineers are left to try and get the most out of this test equipment without consideration of the amount of time they spend to support that as well. Another obvious cost we can mention here is improving of cycle time. If we can do it faster, it takes less operator time, it takes less production, utilization, and you could get your products through quicker. So if you can have a flexible and fast platform, then this is the ideal strategy to be able to test your products. So let's review a typical fault spectrum. We collected a lot of data during our time in the imaging business, and a typical fault Pareto for SMT manufacturing shows that the usual defects of shorts, open, missing, and wrong components, and of course the other process defects, increases as boarding complexity increases, and so does the opportunity to introduce defects. During test effectiveness studies carried out by Agilent, we built a picture of how defects occur. It showed a pattern of systematic system defects versus random. 25% of defects were shown to be systematic in nature that can be controlled and eradicated by process inspection. But that still leaves around 75% of defects that were more random in nature. So if we have 75% of defects that are random and then less impacted by process improvement, then it's clear we need to deploy an effective test strategy that provides optimal test coverage. Here we can look at a typical production line. This area where we're doing the solder paste inspection, pre-reflow inspection, here's where we can be called the defect prevention zone. So we can employ inspection techniques here to try and help us improve the process. Here, generally in the areas of in-circuit test, electrical and functional test, is where test coverage matters. This is really where test coverage saves you money. We call this the defect detection zone. So what information do we need to collect during the manufacturing? So let's examine, first of all, what the information we collect for the repair process. It's clear that during a repair, it's better to repair that PCB during manufacture than we move it further on when we assemble other connectors to it or it enters its final assembly. So if we look at the information provided in inspection equipment, provides the most amount of information to provide repair defect coverage. Then structural test also provides us good electrical coverage, typically from MDA and in-circuit type tests. And functional test provides us information, but less specific actionable information, less specific information that we can use to repair the product. It just tends to say the product's not working for this area and this function. What other information do we need in manufacturing? Well, to be able to confidently ship a product, we need to be able to assure its function. Does it do the job that it's designed to do? With inspection equipment, we're typically not going to just put it through a AOI or X-ray system and ship it straight out the door. It's an electrical product, and we need to be confident that it ships. So functional tests and structural tests give us much more confidence that the product is built correctly and free of defects. However, only a combined strategy provides us both the information we need during manufacturing and also provides us with the confidence that the product is built right. Only by employing a combined test strategy will we be able to have sufficient information to be able to confidently ship a product that's known good and also give us additional coverage for defects that may occur further in its lifetime. In complementary tests, a contribution from technology like AXI and AOI means that the operator can very quickly review the PCB assembly images at different surface mount stages. This equipment uses known good joint algorithms and presents any failure or marginal cases to the operator to review. Inspection equipment can provide a valuable amount of detail to defection processes or components, improve first pass yield to later test stages. But whilst inspection provides a great deal of valuable information, it isn't always so black and white with respect to defect capture. Imaging coverage presents only a subjective view, and electrical test coverage can never be met by imaging alone. Here, let's inspect the image that's shown by an X-ray system. Can you find the open? Could you find the open on this BGA? If you're the operator, could you consistently find the defects? And what about the rework that you do? Touch up or leave it for a later test stage? Remember, every time you touch the board, you can introduce further defects. And also, the cost of rework is expensive. So what about false calls, and what about escapes? Subjectivity kills certainty. When you introduce operators into the equation, then we can never be certain whether those false calls and those marginal calls are real information that we need to action on. So whilst we recognize AXI is a very effective tool to provide quality test coverage into your manufacturing processes, ultimately for close calls like this, it will always come down to the skill of the operator. And this is why we will always rely on electrical test stages to give us the confidence to ship a product. And this is why we employ test stages, because it takes out the subjectivity. In reality, zero defect is more of a dream of the quality department than really achievable. And as a customer, if your production typically falls into the low volume, high mix, you don't always have the benefit and luxury of the data collection and the benefit of the process stability that you can gain from collecting that data. The overall cost does come into play, and it is more acceptable to have overlapping test coverage in a low volume environment. But the defect coverage provided by test stages in low volume is critical and needs to have a high defect detection capability. Typically, this type of manufacturing defect coverage is only achievable from high-end in-circuit test platforms. Complementary test is providing the coverage for the gaps, but we still need to balance visual and electrical. So let's examine the contribution from AOI. We have seen very often that introducing techniques like optical inspection is excellent at collecting those gross defects and really is a benefit to your first pass yields. However, if you employ a strategy that takes from AOI directly into functional test, then you're leaving the functional test to provide the coverage for all these other components like shorts, opens, missing and wrong parts. We cannot rely on AOI alone to fill the gap into functional tests. Functional tests will provide us the confidence, but we leave a gap here where we're giving indirect or subjective coverage for functional tests. Sometimes we employ boundary scan techniques to give us that additional information. But boundary scan is, whilst an excellent technique used for power test and for complex products, it also only has a specific defect spectrum, and it's normally its own standalone PC driven. So we're leaving all these areas, shorts, open, missing, wrong parts, to be able to be detected by other equipments. So let's look at some structural test strategies that we can employ for low volume. Typically, we've seen that MDA or flying probe has been involved. Flying probe is commonly used to detect structural defects, and then additional boundary scan functional tests come in later to provide a more comprehensive structure. This is one option. One other option that we see employed is the MDA tester. It provides just enough test prior to the additional functional test stage. And MDA stages are perceived as a simple testers and sometimes restricted only to less complex PCBs. So let's look in a little bit more detail at the MDA and flying probe stage. So flying probe are primarily used in low volume and MPI. They usually have a higher capital outlay for equipment, but they provide a unique capability to provide test coverage without committing to a test fixture. So in a small volume or for MPI that won't convert to production, they really are one of the only methods to be able to reliably give some level of electrical test coverage. But we've seen very often that some customers are questioning the use of flying probe. And we see the coverage and capability of flying probe can be overstated. Arguments and studies exist that now challenge the utilization of flying probe and question if it really is an effective means to capture defects. On the slide shown above, it demonstrates that from studies and from customer feedback that we've received, that at volumes of around 250 to 300 PCBs per year, then the cost of a flying probe is negated of the cost of buying a low-end fixture. And this doesn't take into any cost reduction or coverage gain by addition of other technologies or techniques into the MDA stage. It's only comparing a like-for-like test coverage, so shorts and open. When other options exist, such as in-circuit test or MDA, at what production volume does flying probe become more of a problem than the one you're trying to solve? Very often, the engineering effort and time is not taken into consideration in low volume environment. But just consider when you're under pressure to take a small batch of 5 or 10 boards through production and into final test stage. If you examine a case of a typical 1,000-node board, the time for this at flying probe would be in the region of 15 minutes for a standard short, open, and analog test. And considering there may be some rework to do, maybe some minor adjustments to the test program during production, then typically this will take around 4 to 6 hours to complete those 5 or 10 boards. And using MDA or in-circuit test stage, test time is in single-figure seconds. So even with rework and some test program tweaking, that batch will be completed within the hour. So equipment utilization and engineer time is really important in the MPI stage, just as well as investments into fixtures. So let's also examine other technologies capabilities that MDA can bring and boundary scan to see if there are any alternatives to flying probe. Here's a typical MDA example. They use analog, have some limited power up for analog, and most MDAs utilize the original test jet invented by HP Agilent in the early 1990s. So why do people use MDA? Well, it's a great platform for low cost and gives some low coverage for gross defects, that shorts, opens, and missing components. And it's here to catch those defects during the manufacturing process. Conventional MDA are a non-powered up board test, and voltage and current measurements are made to individual components, and power is provided by the MDA instead. They generally use a less complex and simpler bed of nails fixture, so that's the advantage that they do have a simpler fixture construction, and they also have a very fast test time. But they still do rely on the bed of nails fixture. So, if not flying probe, how might we employ more test into the low volume cycle? We've highlighted some of the reasons that you might want to reconsider using flying probe test. Since MDA can achieve similar coverage as a flying probe, but at a much lower capital outlay with much more efficient use of capacity and operating time. But however, very often only matching the test coverage of a flying probe can't be just enough reason to move from flying probe to an MDA strategy. So ideally, we want to take a test stage that can provide us low-cost fixturing, coverage and capabilities delivered by an in-circuit test, gives us some capability to combine a functional test, has an easy-to-learn user interface, and can provide the benefit of a fast cycle time, both from the manufacturer of the fixture, but also from the turnaround time of the fixture to get into production. So that sounds very similar to an in-circuit test. An in-circuit test provides a future-proof, single platform basis, gives us some excellent test coverage capability, and also allows us to integrate to functional test, as well as giving us very fast cycle times. However, an in-circuit test platform doesn't directly address the needs for fast turnaround of solution, and very often is not addressing the needs of a lower cost fixture for low volumes. The ideal solution we could look at would be somewhere in the middle, somewhere that can introduce the low fixture costs, but also provide some of the test coverage usually only enjoyed by high-end in-circuit test systems like the 3070, to give us some additional opens coverage, to give us some options for power on, and to give us some options for boundary scan. Typically, these are not employed on MDA. We would call this type of technique MDA+. But why would it be a benefit? If we can gain this additional test coverage from power on, whilst lowering the fixture and other startup costs, we are reaching the level of coverage that improve the capability to detect manufacturing defects earlier and combine other test stages into the same single process. This lowers the implementation costs, and it also lowers the engineering effort needed from later functional stages, and provides levels of test coverage that are getting close to those expected of an in-circuit test system. As you might expect, we have the Agilent Medalist I-1000 MDA Plus system. So we're going to classify the I-1000D as an MDA Plus system. Why do we call it D? Because we also have now capabilities to digital test. This system offers unpowered and power-on test features, and it gives us the true in-circuit test functionalities enjoyed by the higher-end systems. And some of the features I want to highlight are the VTEP version 2 vectorless test. It also allows in-circuit powered digital tests, boundary scan, and also can utilize Agilent's award-winning bead probe and cover extend technology. So let's consider about test coverage. A small difference in test coverage in our defect detection zone can make a huge difference in cost savings. So every percentage point that we can increase in test coverage from a simple test stage saves us costs in real terms in capturing those defects. Just to highlight some of the difference between a typical MDA employment of a vectorless test and VTEP. VTEP was introduced to cover complex devices like BGAs. TestJet was designed in the 1990s to address QFPs, and typically doesn't address these type of devices, BGA, micro BGA, flip chips, and surface mount connectors, whereas whereas VTEP can address these very complex and small package devices. So let's look at TestJet versus VTEP comparison. Typically, the coverage was over 2.3 better in this particular example. We were able to test nearly all of the device, cover 97% of this IC, compared to 41% with TestJet. When we moved to the connectors, we were achieving 58% test coverage of the testable pins, whereas using VTEP, we achieved 98%. We've achieved 445 of the testable 450 pins were able to be measured by VTEP because of the greater signal-to-noise ratio that we have on the VTEP probes. Also, the I-1000 offers a complete boundary scan test. So it can offer tests to do interconnect chains, and ICT and MDA boundary scan do not have the same capability of the standalone boundary scan equipment, but it does provide an excellent boundary scan entry capability at a very low cost. And when you consider you combining other unpowered and powered tests accessed with the real nail pins, then it's a much more effective test vehicle than just standalone platforms. So also the I-1000 offers a complete boundary scan test. Also, every I-1000 is capable with the Agilent award-winning Cover Extend technology. Well, Cover Extend technology enhances VTEP. Standard VTEP is making use of real nailed probe access to stimulate a frequency and measure here at the connector center plate, so we can determine whether there was opens on those connections. Okay, but standard VTEP is relying on test access. If that test access is removed, then standard VTEP is not possible. However, in 2009, we introduced the Cover Extend technology, where we use the signals from the boundary scan device to stimulate the pulses and measure those on surrounding devices. So we can see here an example of those tap signals being put into the boundary scan chain and using the X-test function of the boundary scan to act as the drivers and replacing the need for the real nailed access. And we detect them either on the connectors or surrounding ICs. So Cover Extend can also cover connectors and ICs, and this is available on both the 3070 In Circuit Test system and also the I-1000V. So the RMDA Plus is getting the advantage of the technology that we introduced on 3070. The I-1000 also has capability to test program SPI and I2C devices. So here we can see an example of an Atmel serial flash being actually programmed by SPI. So you don't get this type of capability without adding additional fixture electronics normally into MDAs. So this is another feature why we're saying the I-1000 is an MDA plus. If you look here, the I-1000 digital capabilities are rolling in together the features of a standard boundary scan solution, the features of a programmer, and the features of the digital I/O card that's attached to those. So we see one digital card, one software, and one hardware, one interface can offer the same functionality as these individual solutions. That brings it all into one single platform. And that saves the engineering time as opposed to doing similar repeated tasks using multiple platforms or trying to wedge in different hardware into your fixtures. It's also capable to add in functional test equipment and make calls through GPIBs. So we can also, when required, if we want to bring in tests from functional tests, we can bring those in as well and communicate using I/O libs and the GPIB communication. Whereas some in-circuit test platforms have been criticized for having a long ramp-up time, one of the features of the MDA Plus on the I-1000 is it does have a very simple, easy-to-learn user interface. So it doesn't have all the flexibility of an in-circuit test, but it brings that into a very simple platform and simple user interface. So it does just enough test and also brings in the features of in-circuit test. It has a step-by-step program development. The analog interface is similar to an MDA, very simple page interface for the user. And also, one of the features of a MDA Plus is a digital debug. It's very user-friendly GUI. You can make alterations to the digital test direct from the GUI, and you can look at what the this is a clickable and pullable user interface. It also leverages directly from the 3070 VCL libraries, so you can transfer your 3070 libraries if you do have any historical in-circuit tests as well. So it allows you to easily and simply modify digital tests directly from the GUI. So coming to the fixturing, this is one area where we have an opportunity to save costs. Agilent is well known for its short wire fixtures, so why would we go into long wire fixtures now? So we're not claiming that short wire fixtures are no longer required in today's test environment, and we're not saying that a long wire fixture will perform as good as short wire. The main drive behind this is trying to provide an effective cost solution to the customer at a lower possible cost, not just in terms of the tester cost, but also in operating costs as well. The general assumption is that short wire fixtures usually cost a bit more, as they're generally more difficult to build. But if you talk to some more experienced fixture vendors, that's not the case. They have a good experience building the short wire fixtures used on the 3070. But unfortunately, there's sometimes a cost premium associated with those. The Medalist I1000 offers the use of an MDA type long wire fixture, which are basically targeted for low cost, just enough test requirements. So here we can see there's a very simple fixture base. There is no standard fixture kit that you have to buy from Agilent. The dimensions and drawings are available, so any fixture vendor, anyone can make their own simple fixture interface. It's also compatible with other MDA style fixtures. So this press down fixture is typical of the fixture style that you will see employed in MDA and typically out in some of the Asian supply chains. But we strongly believe that this simple fixture interface can offer a very big cost saving in the low volume and high mix environment as well. And for those, typically these fixtures employ a flat cable connection, and that's part of the cost saving. There's no complex fixture interface. It's directly cabled to the rear of the fixture. If you want to, so one of the disadvantages of that is this changeover time. So if you also need to assure a quick changeover, then we have had some customers who've developed their own adapters, or with partners, there are a number of adapters available that will bring to a more of a standard ICT nailed interface, as you can see here. And this allows us to keep the cost down by using simple MDA type fixture, but also allows us to do quick interchanges. So there's a lot of flexibility in the I1000. And just to examine, do we really achieve the costs from a simple fixtures? Well, a typical fixture kit that we've seen for the I1000 starts around $300. So it's significantly cheaper, and there's no fixed kit, as I mentioned before. So we have a lot of savings on the fixture kit. There's no scanner pins or interface pins. We do have a ground plane, and obviously the amount of probes is the same. Because of the unmux pins, test fixtures can be ordered very quickly, and a simple GUI means that a test solution for a 1,000-node board can be turned around in just a few days. Typically, fixture costs within Europe for an I1000 should be at least 30% cheaper than a traditional in-circuit test. And as more vendors appear in Europe, we expect that cost to drop even further. So when we talked at the start of the web seminar about reducing costs, flexibility was one of the terms we talked about. So we believe that I1000 MDA Plus really allows you to have a flexible approach to test stage, because it can encompass so many things. It can be a simple MDA for just enough test. It can provide flash programming. It can do functional measurements and some elements of functional test, and they're all encompassed into one platform. So there's a lot of flexibility there. So let's recap on some of the I-1000 advantages. It has excellent analog test coverage. It can use the Agilent bead probe to extend the access from In Circuit Test. Also has a digital test, and the signal quality from the digital test is very good despite of the long wire fixtures, because we employ twisted pair within the flat cable and twisted pair within the fixture. So that we have compared, we realize that longer wire fixtures do create noise compared to short wire fixtures. However, the digital card connections from the I-1000 are all twisted pair. And also, we get the same Agilent innovations that have been employed for the 3070 In Circuit Test onto the I-1000 to extend that coverage. So this is how we extend the MDA to an MDA plus, and it provides a much better level of test efficiency in a high mix and low volume environment. But here's an example. We realize that not everybody's going to switch off their flying probe and move to a MDA plus strategy. There's an investment there. But we had a case where a customer were using flying probe. They didn't want to use In Circuit Test because it wasn't a fast enough turnaround and the costs were too high. But they still didn't like the high costs in the system, the time it took for the flying probe, and also the maintenance costs. So ultimately, the time was still meant they had a high cost in MPI. And the test requirements were in the region of just a few hundred nets. Some power test, some boundary scan, and these are the requirements. They needed a flexible fixture structure to really address the cost. They wanted analog and digital test, and they wanted easy programming. So we saw this case quite a number of times, and we were able to create another platform based on the I-1000, which is called the Diagnostic Test Set, the DTS. And you'll see this coming to be released in the next 1 or 2 months, the I-1000 DTS. It's basically all the advantages and interface of the I-1000, same hardware, same software, same innovations, put it into a rack-mountable box. It has a node limit of 256 nets, so it's just enough net for very low node count capabilities. The DTS can also be integrated inside a functional test platform or be standalone. In this case, we've shown the example that we use for one customer, which is a standard mechanical fixture interface with exchangeable cassettes. And this is a very low-cost fixture strategy. So the mechanical fixture base is costing something in the region of 2 to 3k euro, and each cassette then is around 1,500 euro to change. So you can have products turned around very quickly with this simple mechanical fixture interface. The DTS can also be integrated, become part of another system. So you can make individual calls to it using functional Skippy commands. And here's an example of the DTS integrated inside another system. Ultimately, the DTS will be capable to be standalone. It will have an embedded PC card in it, so all you'll need to do is to plug your mouse, your keyboard, and your screen onto it to become a standalone test, or it can become part of a greater test system. So let's draw to the conclusion and highlight some key points. We know that there's a number of test options available, and despite some users' negative experience, Flying Probe does provide the really only fixtureless technology and flexibility for ultra-low volume. We realize that. And if you've already made such investments, you of course want to make the most of them. But I hope that we provided some points to consider that implementing an MDA plus in the low volume and high mix can make sense. So take the time to review what a single standardized platform can provide in comparison to your individual test site. It does provide points of a lower cost. It does provide faster cycle times. It accelerates your MPI cycles. It does have a faster turnaround time for fixtures because it has a simple unmux architecture, and it works directly from the nail file. So you can start building that fixture from day one. So typically we're saying at least 30% fixture cost cheaper than compared to in-circuit tests. So, but there are some compromises required on the aesthetics. It's not as a robust fixture as a standard in-circuit tester. It also provides a capability to rationalize and combine test stages, improving the efficiency of the test area, improving the speed, and means that the test engineer has to spend less time on multiple platforms. Also, because the I-1000 is made by Agilent, it will be tied into all Agilent future investments and future technologies. It benefits from the R&D inputs and efforts that we put onto our standard in-circuit time platform as well. So it's always going to benefit from and leverage from the technology that MSD puts into its R&D investments. Of course, there are many options to save costs, and I hope that this web seminar has provided at least some valid points to consider. I'd like to thank everybody who has joined today, and we're now going to hand over to Derek to take some questions.
Thank you very much, John. So it is now time for questions and answers. Please be reminded that you can send questions now in writing through the Q&A functionality of the WebEx meeting. While the answer to your question may be published for others to see, I remind you that we'll definitely keep your identity private. So let's see what questions we have. Back to you, John.
Okay, thanks, Derek. Just scrolling through some of the questions now. So one question is, what are the advantages of short wire versus long wire, and vice versa? So as we spoke before, using the short wire fixture that's standard on the 3070 system, it does provide much better signal integrity for analog and digital tests. No need to use a twisted pair. And it's a very simple fixture construction. However, the long wire does suffer from more noise, but it allows a cheaper fixture construction, and it also allows us to make more changes and adaptation to the fixture. Okay, so scrolling to the. Hope that's addressed that question. There's another question: how does long wire save fixture costs? And what about signal integrity? As we mentioned, let's touch on the point of signal integrity. Most trying to do powered digital tests through long wires is not a good idea, and that's why we use a twisted pair. So each digital card has 64 pins on MUX pins, and they 128 pin connection, 64 drivers and receivers, and 64 ground. So every other wire is a ground connection. So we provide excellent signal integrity using the I-1000, but it does require that we use a ground plane and also a twisted pair. Okay, just scrolling to the next one. Somebody here like the sound of the DTS and also the I-1000. So the technology is the same, and they're looking for who do they contact for further information. I think because we're on a web seminar, it's better to contact either your local Agilent sales contact, or you can go to the Agilent PCB In Circuit Test homepage. If you go to the agilent.com page and look for I-1000 or In Circuit Test, you'll be directed to the page, and there's a lot of data sheets and technology pages there. If you can't find them, there'll also be direction for your local sales contact from the agilent.com page, or you can contact myself directly. Okay. there's a question here of how many nodes can the MDA Plus support, and what is the max PCB dimensions it can accommodate. So there's no real issue on the PCB dimensions, as big as the fixture can be. You can find that information on the, I don't have that directly to hand, on the fixture dimensions, but the standard size large fixture kits can accommodate, I think, at least over 400, 450 mil PCBs. The highest node count is around 3,500 nodes, so it's a pretty high node count capability of the i1000. There's another question here, and how does CoverExtend work? Surely this is DC from the boundary scan and to the exit. So yes, it's true. We are so the CoverExtend is a power-on test. It provides power pulses from the boundary scan using standard X-test pulses, and measures them on the VTIP. So it's a synchronized pulse. It's not exactly the same technique. You synchronize a pulse from the IC boundary scan, and you detect a difference, a change in voltage on there. So it's a powered test versus an unpowered test. So I hope that addresses that question. There's another question about double-sided access for both top side and bottom side. Yes, you can support that through standard transfer probes or separate cables. I have seen both employed. I think the most appropriate is to use transfer pins from the bottom. It's a more reliable connection. That's the one that I've seen used more commonly. One more question in here, which is, what is the solution for the lowest volume with the highest complexity? And the volume is at 5 to 10 units a month. I think that it's quite a difficult question to address. It's an excellent question, so thank you for that. But it really depends on the overall cost. For the highest coverage, you want the most capable test system and the highest flexibility. So if there are less constraints about cost, then I think In Circuit Test provides a real high-end In Circuit Test provides all the capability to provide test complex boards. We're not trying to say that's different. In a low-mix environment, though, if the cost of the fixture is a barrier, then the MDA fixtures are typically a cheaper option to go, and it can still provide, from an MDA plus strategy, test coverage that approaches an in-circuit test, but they don't have that extra coverage and flexibility capable from a full in-circuit test system, but they do come very, very close compared to an MDA and coverage from different techniques combined, the MDA boundary scan or offline probe. So I hope that's addressed those questions. I don't think there's any more appearing, so I thank everybody for the questions. Excellent questions came in there. And
John, there is one question that just came up.
Okay. Thank you. Okay, so what is the speed? The question is, what is the speed on average board 3070 versus i1000D in reference to analog tests? That's another excellent question. We have not done a benchmark of the i1000 to the new Series 5 i3070. The last one I participated in was from a Series 3. and the test times were very comparable. Some tests were faster, but we did, the I-1000 does do some tests slightly differently, so it was difficult to compare a like-for-like full test to full test. So I haven't participated in a full test, but compared to analog unpowered, compared to the 3070 Series 3, I've seen the test times are almost exactly the same from an I-1000 to an I-3070. The latest I-3070 is faster by around 20 to 30%, but it still provides a very, very fast test time, and also has some different test techniques from some of the diode tests that you can employ on the I-1000. Okay, I think that is almost all of the questions now, Derek.
Great. Well, thank you. Thank you, everybody. Those are great questions. So if you do have any more questions after this event, or you want to ask this offline, please do not hesitate to contact us at the address provided. In a few seconds' time, when I close this event session, an evaluation form will pop up on your screen. So we sincerely appreciate your